Hi, welcome to video 2 of problem solving using data structures and algorithms. In this video or in this lecture, I'm talking about big O notation intuition and algorithm analysis. So basically, we'll look at a few problems and try to understand how do we do the big O notation analysis, which is an important aspect of all coding interviews. And even when you're trying to solve a problem, it's an important aspect of a problem. If you remember from lecture 1 or part 1 of the series, we talked about a template, and complexity of an algorithm is an important part of that template. So we are trying to fill that template, if you remember, and this is the first part of it, which is big O notation. Okay, even before we define what big O notation is, let's actually look at an example where we're trying to find the sum of any n numbers and basically arrive at the motivation behind why we need theoretical complexity. Okay, so let me keep that. I'll come back here. Let's go to Spider here. And I already have the code because if you're familiar with Python, you already know that this is how we find the sum of n numbers. So essentially, let's say n is from 0 to 100. This is going to give me the sum of those n numbers. The first function, which is f of 1, is simply iterating over all the numbers starting from 0, obviously, and going up to n. So range n plus 1 means it goes up to n, and then it's returning the total. Now, the other one, the second function, it is using a formula. So we know that if we are trying to find the sum of all numbers up to n, this is the formula for that. So this comes from our knowledge of math. So this simply takes the value of n and computes this. Okay, so let's see if this runs fine, and then we can go ahead and do something that will help us compare the two algorithms. So there is this function called timeIt. Now, if you're familiar with the time module, you can import the time module and then also check the time that each algorithm takes. But here, this is a faster version. So percentage, timeIt, and then you can do an F1, which is the name of my function, and 100. Okay, let's see how long it takes to execute. So it is executing right now. It took around 4.57 seconds, so that's milliseconds. I can do a timeIt, or even a faster way is using the second one, which is the second function. Let's see how long it takes. As you can see, it gives us the mean and standard deviation of around 7 runs and how many loops each one took when we are using the value of n as 100. Okay. This took 153 nanoseconds, which is obviously way less than the mu seconds. So just by this comparison, we can tell that the second algorithm is better, but this does not work in every situation. Why? Because the time taken by using this actual timeIt function can be a criteria to compare, obviously, but it is most of the times hardware dependent and it varies from machine to machine. So this you might get a different result when you're running it on your computer versus when I'm running here. So we actually need an objective method in which we can compare two algorithms that are independent of any hardware related factors, any external factors. So in order to arrive at that, we utilize something that's known as the big O notation. So that's the motivation behind the big O notation. Now, what is this big O notation? We write with a big O, obviously. So this is how we represent it in terms of the size of the input, right? So whatever the size of the input, what are the number of operations that take place, or how quickly the runtime of your algorithm grows relative to the size of your input. That's the basic definition of big O. Okay, this is important, as we just saw, in order to theoretically compare two different algorithms that are performing the same operation, and we are trying to find out which one is more efficient than the other. Also, as the size of the input grows, it becomes really large. We also worry about the terms that grow fastest with this n. Okay, there are two parts of big O notation. One is the time complexity, the other is the space complexity, and you need to be familiar with both of them. But mostly when we are asking you to find the complexity, it's mostly in terms of time. So let's say you're in an interview setting, you might ask the interviewer whether you're interested in time or space complexity. We are going to talk about both in this lecture. Okay. So as I said, we'll talk about time and space complexity. Let's focus on the time complexity first. By definition, time complexity is measured in terms of the input size, whatever the input size for your code. Um, and it's not based on the exact runtime, which we just saw using the timeit function. So that was the exact runtime, but we need a theoretical way of comparing. So that's what time complexity does. So let's look at examples. Also, remember there are two important aspects of time complexity. Always remember the scale of time complexity and worst case versus best case. Scale means when we arrive at the order in terms of like n or whatever it is, n times something, we have to figure out, or n plus one, or like let's say n plus 2 and so on. We have to figure out of all these terms that are there when I'm trying to find the complexity in terms of the size of the input, right? Which terms are significant versus which ones are the ones that we can discard. Similarly, there could be a worst case situation and a best case situation when we are trying to find the order or the big O notation for an algorithm. Let's go and look at some examples to better understand that, and then we'll come back here. Okay, let's keep this and go here. So I have some examples already here. The first one is a function that takes input as a list, which is of size n. In our case, it's just 5, but this is how we represent n as the size of the input. And notice what it's doing here. It's simply calculating the sum of the first term and the second term. So let's actually go and print this. Now, obviously, I get 3, right? The only thing that can change here is if I change this. And let us assume I add some terms here again, right? So I made the list bigger. And then again, I execute this. I get the sum of the first 2 terms. Okay, so this gives me an idea of why this is order 1 algorithm, because the size of my input, which is n, is growing, but the number of operations that this algorithm or this code performs stays constant. So every time, no matter how large n gets, maybe it gets infinite, the order of operations, the number of operations that my algorithm is performing is constant all the time. It just picks up the first and the second element. It has nothing, the output has nothing to do with how big my input gets. So this is what it meant when we said that the big O notation is relative to the size of your input. So as my size of the input grows, I do not care, my algorithm stays constant, which is why this is an order 1 algorithm. Okay, let's look at another example. Okay, this is a linear algorithm. Why? Because notice what's happening. Again, n is a list, and I'm printing every element in the list. Okay, I get 5 elements, right? Let me create a bigger list, right? And then let me run this. So as you can see, as the size of my input is growing, the output, which is actually proportional to the number of operations that my algorithm performs, is also growing. In like it's proportional to the size of the input, my output operations, which is why this is a linear or order n algorithm. Again, in terms of the input. So all you have to imagine whenever you're trying to do this time complexity analysis is what happens when I make n bigger? How is it impacting my output? In this situation, it's linearly impacting your output, as you can see. Okay, another example. Obviously, this is a nested loop. N is a list. I'm trying to print pair or like all pair of elements. Okay, now what is happening? Let me actually write down this before it becomes, okay, so it's printing all pairs. What happens if I increase the size of this list by just 1? If I increase the size of this list by just 1 element, notice I have these number of operations that increased, like 1, 2, 3, 4, 5, 6, right? So it has an increased 6 number of elements again, which essentially tells me that for every element in the input, right, I go and scan every other element in the input again, which is like n times n. Okay, if this is not super clear, let me actually write it down to make it more understandable. Notice what happens here. I is 1, right? And for that value of 1, when I takes a value of 1, this gets paired with itself, right? Because j also begins from 1. And then this 1 stays as it is because the inner loop executes for the entire list, which is of the size n. And then this stays 1. Then again, this becomes 2, and then the inner loop executes for the entire range n, right? And if you think about these elements, these are nothing but one element in n. So eventually we'll have n operations, and for each of those n operations, for example, here again, it runs for n. For 4, it again runs for n. And notice like 1, 2, 3, 4 constitute the n itself, right? So n times n. The number of operations that we are actually going over when we are executing this function is order, it's obviously quadratic. So, which is why we saw when we increase like a single element, this entire range of values or times n increase, which is why this is a quadratic order algorithm, and it's an order n squared algorithm, right? So this is quadratic. Okay, another example, and this is all time complexity, by the way. Okay, another example, logarithmic. Why is this logarithm? This is slightly tricky, and I have provided a document for you to refer to if you're really interested in the details. However, here we can tell x is some length of the list. So this is my size of the input, right? And this is a while loop. So while loop checks x greater than 0 and then goes and does some operations. This is a constant operation, y equals 2 plus 2. This is going to happen no matter what. But notice what happens to x. My loop gets divided by half, which kind of tells me that I'm not really going and scanning everything. But let's say if I increase the size of my input again. So always, whenever you're doing this analysis, just go and do things to the size of the input to better understand what's happening, right? If I go and increase the size of my input, this loop is going to get into half real quick because x is assigned or reassigned itself by giving this x divided by 2. Okay, so whenever this scenario happens, what actually is going on here is that my input is cut in half each time through the loop. So this takes log n iterations. So let me write it down. So whenever the input cuts into two halves, right, in each iteration cuts in half, it's a log n time complexity because it really comes down to a smaller value quickly. So you can think of it as we are scanning through a list of phone numbers, and then those are already ordered in a certain sequence. So I know that if I'm looking for my name, which begins with U, I don't have to scan the entire phone book. Rather, I can just like go ahead and look in the range of values that begin with U. So that's how I can define this operation as well, that I don't have to scan everything. Rather, I'm coming down to a smaller value, and every time I'm reducing my search, which is why this is a log n or a logarithmic algorithm complexity. Okay, so this was about complexity of some of the important functions. I've again provided more reading in the description below, so please go and check if you're interested in greater detail. Now let's talk a little bit about the scale of big O notation. How do you find the scale of big O notation for more complex values? So as I said earlier here, I defined here, scale means finding the significant versus insignificant terms. Let's look at these two examples. The first one, notice what it is doing. Let's actually write it down. That's always easier to understand. So here it's going and like printing all values in n. Let's say n is a list, right? So just this operation is order n, right? Just this operation is an order n time complexity. Again, this is also order n time complexity, and this is also order n time complexity. So we are bound to think that the complexity of this entire algorithm is order n plus n plus n, right? So maybe order 3n, because obviously we're getting this 3 times. But now the scale actually implies to the cases that what happens when n goes to infinity? What happens when n becomes really big? So does like 3 times infinity makes a difference at all? So 3 times infinity is again infinity. So in situations like this, big O notation is more of a theoretical concept, and so we represent this by just On and discard the constant here. So we have to think in terms of the input again. Always think in terms of the input. In this situation, think about what happens if the scale grows to an infinite value. Is this constant important or not? Okay, so this was one example. Take another example, might be a little more involved in this situation. So let's see what's happening here. This is a function. In the very first, this is a list. Assume this is a list of size n in Python. So this is order 1. Why? Because no matter how large my n is, this is printing the first element, right? Now this is finding the midpoint of n over 2. Now it depends on n obviously, because it goes and checks half of the list and then finds out what's the midpoint, right? So this is order and then n, which is the size of my input, divided by 2, because half of the elements are scanned in order to get this. Okay, now notice what's happening here. It's going and checking for val in n up to the midpoint, right? Go and print val. So print half the values. Again, it's asking us to go and print half the values, order n over 2. Now notice what's happening here. For x in range 5, print hello world. So no matter what the size of my n is, it's going to print this 5 times. So order 5 operations, it's a constant. Maybe sometimes what we do is for things like these, we write O of C, right? So that's up to you. Now the order of this entire algorithm is going to be order 1, right? Plus n over 2 plus n over 2 plus 5, right? So this is like one way of thinking about this problem. Now what happens here is order, if you're really interested in like solving this, the constant term does not really make a lot of sense then, like in a situation when n becomes like really, really big. What happens if n becomes extremely, extremely big? Right? So in that situation, we'll obviously, like, if even if you think about this expression, we'll drop these halves. I don't care, like half times infinity is still infinity, right? And then infinity plus 6 is again infinity, which is why in this case, again, the order of my algorithm is an order n time complexity. So this was about the scale of algorithms. And then finally, we said we'll talk about the worst case and the best case. So before going into the space complexity, let's talk about this function. So notice what's happening here. I have a list as an input and an item. So basically, I want to find out an item, whether it exists in a list or not. Here, I give it a list 1, 2, 3, 4, 5 and ask it to find whether 1 exists in the list or not. So, okay, I haven't defined this. Yeah, so true, it exists. And in the other one, 9 does not exist, so it returns a false. Going inside, we can see that there is a comparison that's happening here, right? So in this situation, what happens when I go and start scanning the list for the first case, for the first example, I find this if condition true for the very first case and I just stop, right? So that's my best case, that I found that element in the very first iteration, and the order of my best case here is going to be order 1. Now the worst case is 9. It went ahead and looped through the entire set of values, list of values, and then it couldn't find 9. So the worst case in this case is order n. We'll also talk about average case later on in the course, but this is something that you might want to point out in certain problems while working through time complexity. Okay, so this was all about time complexity. Let's look at these examples. So again, I've provided you a file that has all this already provided to you. This is a list of all functions and then the commonly encountered big O notation for them, right? And these are, and where C is some constant, obviously. Okay, and a quick look at relative runtime, which we just talked about, versus n. Notice when n grows, how bad is a cubic algorithm, and this is the quadratic. Obviously, we don't want quadratic and exponential at all with bigger values, but notice like for smaller n values, any of these can be a good choice, right? So it totally depends on the size of n. This is a comparison of different types of algorithms for time complexity. Okay, so now coming to space complexity. For space complexity, we are focusing on how much memory your code takes. And it can be similar to the time complexity. It can be very different from time complexity. Let's look at examples again to better understand this and then come back here. Okay, so for space complexity here, what I'm doing in the very first example, just printing for a range of values and printing hello world. So essentially, hello world gets printed 10 times. Obviously, the time complexity, which we just talked about, is order 10, right? But what happens if I increase n to 100? It will print hello world 100 times. The space that it takes, so the thing that I'm using for actual space is assigning some memory location to this hello world. That does not change, right? So the time, the space complexity for this is order 1, right? So here it does not change. I am just creating a single variable and saving it somewhere, which is hello world, and then obviously accessing it again and again. So it's taking more time, which is why the order n time complexity exists, but the space complexity is order 1 in this case. Okay, let's look at another example. So here what I'm doing, again, I'm a little bit similar, but notice I'm creating a new list. And again, adding values based on the size of n. Now, we might argue that here, but just like look at the difference between this and this. So we're not really printing anything just by allocating this element to a memory. Rather, we are appending this, whatever constant it is. For example, in this case, it's new, and I'm appending it to the list. So depending on the size of my n, the memory that's allocated to the list will increase. What I mean by that is, let's say the size of the list was 10, it will have these 10 elements, right? It is growing. What happens if I give it size 15, right? I'll have a bigger list with 15 elements. Also, although the elements have the same value, does not matter. So imagine that the memory allocation to this increased. So in this case, the space complexity is order n. And in this case, it's order 1. So there is a subtle difference, but yes, that difference exists. Okay, so this was the basic difference between space complexity and time complexity. Because we are working with Python, quick things to remember. So this is about the lists, data structures, and these are some of the operations that we do with lists. Notice with indexing, it takes just order 1 operation. These are actually dynamic arrays if you are familiar with other languages. So lists are dynamic arrays in Python, and these are different operations that we've been working with when we write Python programs. But here is the big O, time efficiency. So maybe I should have put here, these are the time efficiencies. So whenever you use any of these operations, make sure that you know the time efficiencies. If you're familiar with Python dictionaries, right? So these are nothing but hash tables. Again, we'll talk greater detail about hash tables later on, but just to give you an idea of some of the operations that we do in dictionaries. So for example, for copying, it's order n. Getting and setting an item, deleting an item is order 1. Iteration is order n. And as if you're familiar with hash tables at all, these, like most of the operations, are way faster. Most of the operations have a constant value, which is order 1. And I would add to this dictionaries and sets. Both are hash tables in Python. So we'll talk more about them when we go into the greater detail. But this was all about Big O notation in terms of technical interviews. Just remember the template we talked about earlier and fill in the complexity part using the ideas that we talked through in this video. Computing and just like reviewing, computing and discussing the complexity of a solution will come up, right? So you should be able to identify the time and memory, and it's really good if you're able to differentiate between the time and a memory or complexity in every algorithm and able to point out the difference, right? And it should not take you a long time because we just saw some techniques of trying to find out using some examples, right? And just remember, no complicated math is expected. You are just you should be quickly able to visualize the moment complexity question is asked based on the input size. Always remember that, right? So there's no complicated complex math involved here. If you have questions, any doubts, please ask in the comment section. And I have also provided in the description box some greater details and additional resources. Thank you.